Okay, when you're looking at molecular geometry, you want to keep separate the electron domain geometry from the molecular geometry. So if you have a molecule and you've drawn the Lewis structure and you've got some element, it's got some number of bonds associated with it, and you just maybe start by putting the bonds in there, maybe you've got a lone pair or something. First you want to analyze the electron domain geometry, because that will help you to realize how many groups of electrons there are that are repelling, that are causing each other to spread out from one another because of that repulsion. So first you want to analyze, okay, I've got a lone pair, I've got a bond here, I've got another bond here, I've got another bond here. So that's 4 groups. Maybe I have a different situation where I've got a lone pair and a double bond and a single bond. So remember, a double bond counts as 1 group. So that would be 3 groups. So first figure out how many total groups of electrons there are, because if I've got so many groups of electrons and they're spreading out, that's going to cause them to spread out either more if there are fewer of them, because there's more space for them to spread out in, or they might be bunched together more if there are too many and they have to be crowded in to fit the number of electron groups that you have. So if you have, so for number of electron groups, if you have 1, then you don't have to worry about it, because that is an atom that's only bonded to one other atom. It will always be linear, and I'm not going to ask you to label the geometry of it anyway. So at the minimum, you're going to have an example with 2 electron groups. You might have 3, or you might have 4. So there are different situations, but if you have 2 electron groups, then the electron group geometry is going to be linear. If you have 3, it'll be trigonal planar, and if you have 4, it'll be tetrahedral. So we saw what those shapes look like, what the angles are: 180, 120, and 109.5. And we know the angles might deviate a little bit because some of the electron groups repel a little bit more than others and cause things to spread out from them a little bit more. But roughly the angle should be close to that. So what are some of the options for arranging the electrons to create these situations? So if I have, so for two electron groups, that could be a situation where I have an element like beryllium that is not going to have 8 total electrons around it, where it will maybe only have 2 single bonds. 2 electron groups are going to spread out. The other option might be a rare situation, but I might have 2 double bonds on either side of something like carbon dioxide. That will also be linear because I've got 2 electron groups. Another situation is I could have a triple bond on one side and a single bond on another. That carbon will also be linear because I've got 2 electron groups. So a double bond, a single bond, a triple bond all count as 1 electron domain or 1 electron group. Another option could be maybe I've got a triple bond and a lone pair. So again, if the atom's only bonded to one other atom, then I don't really worry about labeling its geometry. Right? So really these are the only 3 situations you might have where the geometry would end up being linear. So it's much less common than the other geometry. For the other options, so if I have an element like boron with 3 single bonds, because we know boron, even though it won't make an octet, may bond to 3 things to balance out its formal charge and avoid an unstable formal charge. That's going to be 120 degrees. I've got 3 electron groups. More often than not, one of my electron groups will be a double bond, because if I have a double bond and 2 single bonds, to whatever elements. Now my element X has 4 total bonds, which is a noble gas configuration. So that's more common because it's a little bit more stable. So these are both. So I want to label the. I don't have a lot of space here. Molecular geometry. So I'll label the molecular geometry in red. So these are all linear. These are both trigonal planar. So when I have a situation where my central atom has a certain electron group geometry and the central atom only has bonds and no lone pairs, then the molecular geometry will be the same as the electron group geometry, because the molecular geometry is meant to show the shape created when atoms are bonding at each of the positions and to look at where the atoms are connected. So if we're looking at where the atoms are connected and there's an atom connected at the end of every electron group, then the connections that atoms create will create the same geometry as what the electron group geometry is. If I have a situation where I've got a lone pair on X, and now maybe I have 3 electron domains. So the electron domain group, since the lone pair takes up space, is trigonal planar, because I've got 3 electron groups. But in this case, if I'm looking at where the atoms are located, the shape created by that is bent. So those are the most common situations you'll end up with when you have 3 electron domains. If you have 4 electron domains, that could be a situation where you have a group. Carbon does this a lot. 4 single bonds. If you have an atom at the end of each bond, then it's also tetrahedral, because tetra means 4, and tetrahedral shape is a shape with 3-dimensional shape with 4 sides. If you have one of those as a lone pair, though, so that probably wouldn't be likely to be a carbon, but some element with a lone pair and 3 bonds. I've got 4 electron domains, so the angle here is still 109. The electron group geometry is tetrahedral, but if I'm just looking at the shape created by where my atoms are located, now I've got something that looks like a pyramid. And I've only got 3 atoms attached. So the molecular geometry here would be trigonal, because I don't have 4 atoms attached, pyramidal. And then the other option would be, so if I have 2 lone pairs and 2 things bonded, again, the angle is still going to be about 109, because I've got 4 electron domains total, all repelling, and they have to spread out. The best way for them to spread out is 109-degree angles. But in this case, if I just look at where the atoms are, I get a bent geometry.